Hi, I'm Ben-Yaakov. This presentation is entitled DCM Peak Current Mode, Behavioral Average Model, and a Worked Out Flyback Compensation Example. I'd like to thank Anthony Wood for raising the flag on this subject in a LinkedIn post. And there is a disclaimer here that the commercial devices that are shown in this presentation are for educational purposes only. There is no endorsement or recommendation implied. So what is a peak current mode? In a peak current mode, the modulation is done in sort of a different way from a voltage mode, in that we have a clock which is triggering a flip-flop turning on the transistor. It's a MOSFET. Current starts rising, and then we have a reference level here. And when this current is hitting this reference level, the flip-flop is reset and the voltage of the gate is off. So what we have here is that the peak value of the current is following the reference level, so that if this reference level is, say, increasing, then the peak will follow it. Okay, so this is the peak current mode. Here I'm showing an implementation in a boost converter of a peak current mode. This is a boost converter, inductor, switcher, and diode. And here we measure the current. This is the current of the inductor while the transistor is on. We have a filter here. This is in order to damp or filter out this peak arising from the injection of a current while there is a rise in the gate voltage. There is a current coming here through the gate to source capacitor. So there is a spike here. In order for it not to interfere, usually there is a filter here to suppress it. Here we have a comparator, and this is the flip-flop, which is turned on by the clock, set by the clock. And then we have a feedback here from the output through a divider, comparing it to the reference. This is an error amplifier. It's a compensation here. We'll talk about it. This is the reference level here, to which the current of the inductor is compared. Once the current approaches the reference level, the comparator flips over, and there is a reset, and the transistor is turned off. So this is a typical application of the peak current mode, which has many advantages to it. Two of them are that, first of all, it is a cycle-by-cycle protection of the current, because if the current is hitting the reference level, transistor is off, so it's like a natural current protection. A second advantage of the peak current mode is that it is actually turning the second order system of the boost converter into a first order system, which simplify the compensation, that is the feedback through the output. And what we have here is a flyback. This is the transistor. Here's the output section coupled to the primary. We have the transistor, the driver to it. We are measuring the current across a sense resistor at the source. Here is the comparator. We have a clock turning on the flip-flop, setting the flip-flop. We have feedback. I'm not showing the divider, etc. I'm just indicating there is an error amplifier, and the compensator will be here. And then the output is the reference level to which the current is compared. And when the peak is reaching this value, the flip-flop is reset and the transistor stops to conduct, and the output now is discharging. Now we can see it here. These are the gate signals which are generated. They are not forced, they are generated by the current. The initial transition is caused by the clock. The inductor current, primary, is increasing, reaching the level set by the error amplifier. Once it's reaching it, then the gate is turned off, And at that time, of course, the output now sees the current. This is a transition here. And we are talking about discontinuous mode so that the current is going down to zero. There are many controllers of Flyback and other topologies. And here I'm showing one by linear technology, now analog devices. Again, this is just an example. This is a constant frequency current mode Flyback DC to DC controller. And it is now a unit which includes a driver to a transistor. It's an outside transistor. Here is the sense resistor for the current. This is now the feedback. Inside we'll have the error amplifier. This is the compensation network. We are going to talk about it. So this is an upper level controller which has many functions in it. We can then realize this Flyback converter. Now the internal structure of this unit, this is a simplified, of course, block diagram. We can start from the error amplifier. This is the output, a divider. This is the error amplifier. It is a transconduction amplifier. That is, the output is a current rather than a voltage. It's not a voltage to a voltage, but a voltage to a current amplifier. Here is the compensating network. This is now the comparator. The clock is here, 300 kilohertz, setting it. And again, this comparator will reset it when the output will reach the current of the inductor, in fact, which is sensed by this resistor. Now, this particular unit has the option of adding here a resistor, which is used in order to implement what the so-called slope compensation, which we do not need in DCM. This is required in CCM with duty cycle about 0.5. This is a different subject. I'm not going into it. So in this case, we really don't need this resistor. Okay, and this resistor, by the way, is fed by a slope coming from the oscillator. Again, this is not relevant to our discussion. So now, if we examine a DCM Flyback in which the current goes up to a certain level and then down, we can find out what is the energy per cycle coming in from the input. The energy will be the energy stored in the inductor at the peak instant, and this will be I peak squared times L1 over 2, and the power which gets into the system will therefore be this energy in joules times the frequency, the switching frequency, and this is for a fixed frequency situation. So we have an output to which we pump energy, okay? And what I like to do, I like to build an average model for it. This is the objective of this presentation. Now, we do not have a native power source in, say, LT-Spice, which I'm going to use. So what I'm going to do, I'm going to replace this unit by a current source such that the power delivered to the output will be the required one. To do that, I need a current source that will be defined by the required power divided by V out, okay, by V out or V out here. So the power now is I times V out. I is P over V out times V out. This will be P, that is the power. So this is a way to actually generate a power source with a unit that LT-Spice and other Spice and other simulator will accept. So the output power is equal to the input power, and if we want to be more accurate, we multiply it by the expected or estimated efficiency, and then it is equal to the I peak square L1 over 2, then times the frequency, and again efficiency if we want to correct for rate. And therefore, this will be now the current source, the dependent current source, I peak square L1 to V out, frequency times efficiency. Of these, this is generated within the simulation run. This is a constant, this is a constant. And V out is also a time-dependent parameter that is changing as the simulation goes on. Looking now at this unit, we understand now that we have an error amplifier which is external to the behavioral model I was talking about. And then we have the connection or relationship between the voltage here and the peak current that will evolve. Now, as you can see, they have here something which is not clear what it is. That is, the value of the reference is not just the voltage here, but there is some adjustment here. So since I don't have the information on that, then I assume that there is another transfer function between the output of the GM amplifier and the actual I peak. Usually the I peak will be sort of clamped to this value. But here there is something here which is not known. Here now I have already the output current. This is actually a power source, okay, defined by these parameters, all are known. What I don't know is this thing here. What is it? Now, this output here, comparator, is given. It's here. This is the value. This is the output of a GM amplifier. So what I'm going to do, I'm going to take the jig provided by Analog Devices in LT-Spice of this unit, okay, in a flyback converter, and I'm going to actually test it and find out what is the relationship between the voltage here and the peak current. Sort of a simulation experiment, okay? For that end, I'm going to clamp it to a voltage source. So I'm forcing a voltage here. That's okay because this is a transconductance amplifier with a current output. So no harm done. And I'm going to sweep it throughout the range which is expected. And I'm going to watch the peak current here and see what is this relationship. So here is what I got. This is the excitation, this is the sweep. This is the inductor current. It's a high frequency. We don't see the actual current. We just see the boundary of it, okay? What we see clearly is that this is a nonlinear relationship. That is, the slope is not exactly as this slope, and there's also an offset here, okay? So the excitation obviously is affecting this, but there's sort of a relationship here, which I have found that it can be expressed by this equation. It's a linear equation. This is now the voltage coming out of the comparator. This is now the average model, okay? What I have here is this is the transconductance amplifier. This is the output. This is the relationship between this output and the actual reference used to compare it to the current. So this is the actual value here of the peak current, because the peak current or the current will reach this value. And then I have this definition of the output current, which is shown here, I square times the inductance, turns out to be 50 microhenry, times the frequency, divided by the value of the output voltage. Okay, this is what we need here. I'm using absolute, so if it's minus, so it won't be confused here. Also, since I'm multiplying the current, then if the current is negative, this will always be positive, which is not good, because then the simulator might lock into a wrong position. So therefore, I've added a sign here. I didn't find a operator for sign, so I did it by taking the current. This is of course the voltage representing the current, times the absolute value of it, so it's a plus minus 1 depending on the sign of the current. Okay? And then I'm also doing the same experiment here by having this source here which is sweeping the same way I did it with the actual circuit. And then I didn't say that, I'm also clamping the output so that the discharge will be around the operating point, because if the voltage is very low, this will not represent the actual situation. So I'm sort of forcing an output voltage which is the stabilized voltage, and this is also done in the actual cycle by cycle simulation I showed earlier. And here are the results. So what I see here, that this is the excitation, and this is the actual peak current, or the current, and this is the peak value here, found from the cycle by cycle, from the jig, from the actual simulation of the unit, the time domain simulation. And this is the result of the average simulation. This is after the fitting with the equation I've shown earlier, and you can see that the peak value is pretty much, or I'd say very good match, within some error here, which I didn't close, to the average. So the average response now and the actual response of the time domain simulation are the same. So now I can actually test my average model against the cycle by cycle or time domain model provided by LT-Spice. And what I see here is a response to a load step. What I did here, I've added a current source, a pulsing current source, and in this case it's 0.5 amp. This is done here and in the actual LT-Spice model, the time domain simulation. So what I see here is the response of the time domain simulation. Obviously I can see here the ripple at the output, and this is now the response of the average model. And as you can see, this is very good. A very good match between the average and the time domain simulation. I can see here that the response has some overshoots here, well, sort of oscillation or close to oscillation. This jump here is due to the ESR, but then I have here sort of a on the verge of oscillation. Okay? Now the compensation that they have put, I'm showing it in the behavioral model, the average model, but this is the one that is shown in the here. Okay, this is the actual jig, the original one. So in this case, this is only a capacitor. I've just put here 10 milliohm, which doesn't do much. Okay, so this is rather a poor compensator because it has only a pole. It's not a lag lead compensator or a so-called type 2 compensator, which is needed if you have a first order system as you would have with the peak current mode. So now I can do something which is possible with this average model and not possible with the time domain model, and that is to get the AC small signal responses. To this end, I've put here an AC excitation by which I can get the responses from one point to another, and in particular, which is nice, I can get the loop gain in closed loop, because if I look at this signal, I can see that it's going all the way and then it's coming back here. So therefore the ratio between the voltage here and the voltage here is in fact the loop gain of the system. So this is the main power of average model, that you can get the AC response, the small signal response around the operating point, which is very important for optimizing the compensation network. So here it is. This is now the loop gain. This is the gain, and this is the phase. I'm looking at 0 dB gain and the corresponding phase at this frequency, which is 2 kilohertz. This is the crossover frequency. And what I see here, then the phase margin is indeed very low. It's about 19 degrees. So this explains this oscillation that we get due to a load step. Okay? So now I've modified this compensation network by adding now a 50 kilo ohm, which makes it a leg lead or a type 2 compensator. And in this case, here is now the loop gain again. Now the crossover is here. This is, well, 1.5 kilohertz perhaps. But the phase, look at the phase, it's 90 degrees. So this is definitely a much stable situation. Although the 90 degree is a little bit too much perhaps, it'll affect a little bit the response. So let's have a look at it. And here is what I see. This is the original response, and this is with the modified compensation network with the 50 kilo ohm. This is just a capacitor. And you can see that indeed there are no oscillation here, but the response is a bit sluggish, and this is because of the phase margin, which is 90 degree. In fact, a smaller phase margin will kind of make it faster response. So indeed, by changing the resistor to 30 kilo ohm rather than 50, I can change it to this response. There is a very slight overshoot here, which is okay, but you can definitely see that the recovery is much, much faster than it is here. So this will be a much better compensation situation. But there is another point here. If we look now at the pulse stage itself, which I can do by simply looking at the ratio of the output to the input here. This will be the pulse stage, okay? So with the AC simulation, I can get the pulse stage response. So what I see here is indeed this about first order response, the phase approaching 90 degree. This is 20 dB per decade. But then, due to the ESR of the capacitor, and they have put here a 300 microfarad with a 50 milliohm resistance, it's built in, I get now a 0, which makes this response now flat, and the phase is now approaching back 0 degree, because this is just a resistor, ESR. It is fed by a current source, so it is just a resistor. And therefore, if the switching frequency is high enough, and it is 300 kilohertz, and half the switching frequency is 150 kilohertz, which is about here, I can actually close the loop here, which is at a much higher frequency that I had it before. So the response would be much, much higher. Now I'm showing here what I called 1 over beta. This is a method that I'm using in order to examine and design the compensator. And you can look up, I have a number of videos at YouTube which are explaining this approach. So by changing the compensation network to merely 50 picofarad, which will make the trick, because all that I need here is indeed, in this case, just a pole. And then in this case, I'm getting a crossover frequency of 6 kilohertz rather than 1.5, and getting a phase margin of 34. I didn't try to tune it to better than that, which is pretty good. Normally you would like to have, say, 40, 45, but this is pretty good. And here is the phase margin, I can see it here. So in this case, the response is much, much better. You can see that it's a very fast response. We primarily see the drop due to the ESR and then a very fast recovery as compared to the original response, which you can see here, which is of course much, much worse than this. Now zooming in, I can see here both the average model and the actual cycle by cycle simulation done by the LT Spice and the model they have. And first of all, you can see very nicely the matching of these two, and you can see also that in the time domain the response is very, very similar to the average one. So the average model is really showing the average behavior of the peak current mode DCM flyback converter. So what is the conclusion here? Average modeling and simulation is really a powerful analysis and design. I try to show that you can build a average model of a DCM peak current mode very simple. One should be aware of course, that a good practice is to design the compensator over the expected operation envelope. I've shown the response at one operating point, and of course one has to look at the extreme points and make sure that throughout the envelope the system is behaving as required. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.